Okay. Guess I'm ready to continue. Okay. So what we're doing is we're looking to model the solution as an expansion where the leading order term So to a first approximation, z would be q, but turns out we'll need these this finer structure. So you have this leading order term, and then beyond that, of course, it's not an exact formula. You wouldn't expect it to be an exact formula, so you need an extra second order term, and so you could add w, or what's just equivalent is to leave the phase and the scale on the outside, and do it like this. So now w is that w would be the next order correction. And in fact, it's, by putting the scale on the outside, that's how we make the reference point, the lambda equals 1, significant, because lambda is going to 0 as we blow up, so we're actually moving in the lambda direction dramatically, of course. But if you're going to pull back by the lambda action, then you can make lambda a neighborhood of lambda equals 1 as the important reference point. But the problem with this expansion is that it doesn't reduce the problem to understanding the evolution of w alone. It also, we still have to understand what, there's still unknowns. Gamma, lambda, b, and beta are still unknown. And so the leading order term should really be thought of as not a point in phase space, but a four-dimensional manifold. And that's what led us to this discussion of symplectic projection. So let me motivate it a little further. We talked about NLS as a Hamiltonian system. How about we just return to classical mechanics, in which n is equal to R4. Let's say you need an even, so it's 2d for any d you like. But if we take R4, and then the metric would be just the dot product, right? Then you take J to be the matrix, the block matrix 0, identity minus identity 0. So that's the 4x4 block matrix. Then what you get is classical mechanics in canonical form. So you consider the point, so R4, x and y, we should use x and y. We should use Q1, Q2, P1, P2. And then the equation, the Hamilton's equations would be Q1, Q2, P1, P2 dot, so the time derivatives, equals J times the gradient of a Hamiltonian. So that's going to be this matrix times just the vector of derivatives. And so that gives you dH dP, dH dP2 and minus dh dq minus dh dq 2. Okay. All right, so for example, you could take h to be h of qp to be 1/2 q squared, 1/2 p squared plus v of q, and that gives you the standard mechanics. Now imagine that Q1 and P1 represented a submanifold for us. So this would just be Q1, P1. And we were studying a flow in the 4-dimensional space that remained close to this 2-dimensional submanifold. So we have some flow out here, and points we want to project onto the submanifold M. So there's a Q1, P1, Q2, P2. Then why is symplectic projection the right thing to do? Well, if the Hamiltonian system were in this nice form, this so-called canonical form, then you would see that if you happen to know that the point was close to M, then that is saying that we happen to know that Q2 and P2 are small. And so if we look at the equations here, this is H is evaluated at Q1, Q2, P1, P2. But to a leading order approximation, Q2 and P2 are approximately 0. So this is at Q1, Q2, P1, P2. This is approximately 0, approximately 0. And so the projected dynamics should be, to leading order, the Hamilton flow of the restricted Hamiltonian. So you take H, you just evaluate it on M, and then you just compute Hamilton's equations on M, and that will give you an approximation to what Q1 and P1 are doing, without knowing so much about what Q2 and P2 are doing, except that they just remain small. So that's how you can kind of understand parameter evolution without having a full understanding of W. Okay. Right. Okay, so I have to continue with NLS here and motivate the introduction of Z. So we start with Q as our primitive approximation. And Q solves this equation. It is convenient to observe that that is the stationary point of the functional A, which is just the mass plus the energy. All right, because if I look at what is A prime of Q, that is M prime, so it's M prime of Q. Well, let me just, A prime of U is M prime of U plus H prime of U. And that is just U minus Laplacian U minus U to the P minus 1 U. So A prime of Q is equal to 0. So in fact, at the level of evolution, we can transfer from Hamiltonian H to Hamiltonian M plus H2. We just take dtu equals j H prime of U and you let v equal to e to the it u of t, then dt of v is, is it minus? Yeah, so it's minus. Is then j of m prime. This is j of, yes, it's just j of a prime of u, of v. Right? So it's just time differentiation just gives us a minus I term, which is j times m prime. So it's just to show, right? So really expanding u would be equivalent to expanding v. And then we have that a prime of q is equal to 0. So if we want to write v, so ignoring the parameters for a moment, let's just say we want to study solutions to the v equation in a neighborhood of q. That would be writing v equals q plus w. And then you would have dt v equals, dt plugging into this equation gives you, q is now stationary, so it's dt w is equal to j a prime of q plus w, which is j a prime of q plus j a double prime of q w plus O of w squared. But j a prime of q is equal to 0. So then the equation for w would be dt of w equals j a double prime of q w. And that's what we call linearization of NLS around the ground state. So dtw, so of course we've dropped all the parameters in the problem, we have to add them back, but this gives you the first understanding of what's happening with w. Is the linearization of NLS around q, around the ground state. So what is a double prime of q? Well, it's so a double prime of q is m double prime plus h double prime, and I wrote down h double prime before. When you plug in u equals q, q is real valued, so that actually simplifies the h double prime a little bit, and so you get a double prime is the operator identity minus Laplacian minus p plus 1 over 2 q to the p minus 1 minus p minus 1 over 2 q to the p minus 1 times complex conjugation. And what as Weinstein was writing the papers in the 80s on this, and he preferred the real imaginary decomposition rather than the WW bar decomposition. So that's what's stuck. So most people write this as L plus of the real part plus I L minus of the imaginary part, where L plus is 1 minus Laplacian minus p q p minus 1, and L minus is 1 minus Laplacian minus q to the p minus 1. So that gives you two self-adjoint operators whose properties are relevant to the analysis of the linearization of NLS. The linearization of NLS is this j times a double prime of q. So the presence of j here takes us outside of the self-adjoint world. It's no longer self-adjoint when we look at the full linearization, the J A double prime of Q. Okay, so we have, I'm going to leave that there. So we have J A double prime of Q W. Once you multiply that by minus I, you get this. And now if you pass to real, so take real and imaginary. Then you would get dt of the real part, imaginary part, is equal to 0 L minus minus L plus 0 real and imaginary. And this can be written as J times, so this can be written as a new J, L plus L minus. As J is no longer multiplication by minus I. I mean, we took real and imaginary parts. Now J is a matrix, is the standard skew matrix. So J is now the matrix 0, 1, minus 1, 0, if you do it like that, right? But you see from this that the operator here that we're looking at is definitely not self-adjoint. It's not even skew adjoint. It's actually non-normal. So its spectral properties are very subtle. So one often passes to real and imaginary parts like this to get a 2-by-2 system rather than working in the original form, because to do spectral theory, you have to work in a Hilbert space over C rather than over R. So you have to complexify, but you had an I here, and you don't want to confuse this I with the I that results in complexification. So you have to first pass to a 2-by-2 system, and then you complexify. So now real part of W and imaginary part of W just become two functions with values in C, and you want to understand this operator. So what we do is we compute the spectrum of this operator. Well, at least we understand the kernel very well. We compute the spectrum of this operator. And what it shows us is that there are these two directions corresponding to B and beta that we forgot. So the first thing we try is you put a Q here, and you look at Q plus W. You then compute the equation for W and look at its spectrum, and then that showed you that there are the two directions that you really should have included in the leading order. And so you add them back in, and you try again. So that's how I'm motivating it, I guess. But the spectral analysis of this is very nice. So Weinstein wrote these papers called modulational stability of solitons. Because this also shows up in the study of solitons. So solitons are unstable in this critical case, but the analysis of blow-up is the application in the critical case. So Weinstein. Let me write it over here. So to get the spectrum of that operator, you first start by understanding some of the mapping properties of this A double prime. So the first thing you do are some computations. Just give you a flavor of it. So I'm going back to this form of writing things because it's actually more convenient for doing computations at this level. but ultimately when you talk about the spectrum, you have to go to the 2x2 system. So we can in fact compute 5 mapping properties just by exploring the effect of modulating and symmetries. Okay. So recall that lambda, yeah, I guess I started using y here rather than x. There's a reason for that, because ultimately what we do is we take y equal to x over lambda, and so, yeah, so let me just stick with the y so that I don't get confused with my notes. Right, so this is actually, these are all equivalently phrased as mapping properties of L plus and L minus. This is saying, for example, that L minus of Q is equal to 0. This is saying that L plus of gradient of Q is 0. This is saying L plus of lambda of Q is minus 2Q. And this is L plus of YQ is minus 2 gradient of Q. L minus of y squared Q is minus 4 lambda Q. So I'm doing the full analysis here without the radial symmetry assumption. Once you restrict to the radial subspace, then this and this would not be important anymore. You would be working orthogonal to them, but I'm just including them for now. All right, so this is the information that you want to use in further analysis of this 2x2 matrix operator. But they're most easily derived in this form, because you can just read them off of symmetries. For example, so for the proof, I'll just do, say for the first one, what you consider is the one-parameter family of functions, call it Q sub gamma of y, which is just, it's just e to the I gamma q. Right? And then you recognize that A prime of q gamma is equal to 0 for all gamma, because the phase just comes out. And so therefore, you can take the derivative. So you take the derivative with respect to gamma and set gamma equal to 0. And it's still 0, but this becomes a double prime of q evaluated at 0, and that's q. Applied to, so that's an operator, then applied to the derivative with respect to q, which is I times q when it's evaluated at gamma equals 0. Right? So that's it. And that gives you the first mapping property without. So the other ones, like the third one, where you actually don't get 0 as an answer, that's because the third one, you look at q sub lambda of y equals, say, lambda to the d over 2q of lambda y. And then you can compute that this solves the equation lambda squared q minus Laplacian q minus q to the 4 over d q equals 0. So for lambda in each place. That's just how the scaling behaves. So written out, this is the equation lambda squared m written in functionals. There's lambda squared m prime plus h prime. And now you take d lambda and evaluate at lambda equals 1. And what happens? Well, when the lambda derivative goes inside the functions, like m prime and h prime, then you get m double prime and h double prime. Then you evaluate at lambda equals 1, you get a double prime of q, evaluated at the derivative of lambda, q lambda, lambda equals 1. But then there's the lambda on the outside as well. So there's an extra term. And that's what gives you the 2q in the resulting formula. So that's it's using symmetries that gives you the easiest proof of these mapping properties. Okay, so once you know what once you have these mapping properties, then it turns out one thing you can do is for L plus and L minus, we know that L minus of q is equal to 0. So that's telling us that q is in the kernel of L minus. But q is positive. It doesn't have any zeros. And so the Sturm oscillation theorem says that q must then be the lowest eigenvalue. Q must be 0 must be the lowest eigenvalue. And the lowest eigenvalue is simple. So the corresponding eigenspace is just spanned by q. So that tells us that the kernel of L minus is q. And L plus for the gradient of q, so the gradient, so the derivative has 1, 0. And so actually there is a negative eigenvalue for L plus. And then the kernel of L plus is spanned by the gradient of q. And then you see that you have an L plus mapping onto the q. And so what this, I shouldn't have erased it. So what we want to understand is this j a double prime of q, which was 0. Let's get it backward to L, 0, L minus, minus L plus 0. That was it. So you can build a vector, right? So you first let's call this L. You first note that 0q is equal to L minus q, 0, which is 0. So 0q is an element of the kernel of L. But then you also have something mapping to q. You have this L plus of lambda q giving you minus 2q. So actually, if you put a lambda q here and a 0, then you will get 0 minus L plus of lambda q. So you'll get a 0, 2q. And so that maps to the first one. So this kind of analysis is what leads you to a full description of the generalized kernel of the non-normal operator L. And this is all in Weinstein's paper. So the spectrum of L, so if I draw real and imaginary axes, turns out the spectrum of L goes, there's continuous spectrum from plus I up to plus I infinity, and minus I down to minus I infinity, and then there is 0, the generalized, people say generalized to emphasize that it has a Jordan block structure kernel. And it's the structure of the kernel that is important. It's effectively the main source of instability for this problem. And it is exactly by modulating on the parameters that we can project, we can arrange so that W is perpendicular in quotes, because it's, I have to explain, it's not normal, so it's perpendicular to the kernel. It has zero projection onto the kernel. Okay, so and this kernel, so I showed you a sampling of how you start to figure out what the kernel is. So the generalized kernel is n of L. N of L is spanned by if you set it up with proper normalization, then you get some funny fractions showing up. But I'll just write the answer. There's Q1, Q2, Q3, and P1, which is 1/2 rho. Rho is defined to be L plus inverse of y squared Q. And such a thing exists. You can check that this is orthogonal to the kernel of L plus, which is spanned by the gradient of Q. 2 alpha, and alpha is just a constant that P2 is 2 lambda Q, and P3 minus 2 gradient of Q, 0. All right. All right, so the generalized kernel is spanned by these 6 functions, and actually there's y here and a gradient here, so this is actually d-dimensional, and this is d-dimensional, so it's really a 4 plus 2 d-dimensional kernel, but it's really a Jordan block object. It's if you the L, I have a diagram here which shows you how L maps P1, P2. But if you apply L to P1, you get Q2. And then if you apply L to that, you get P2. And then you apply L to P2, you get Q1, and then you finally get 0. And then Q3 maps to P3, which maps to 0. And alpha is just a special number, which, if you're curious, it's rho y squared Q over 2 yq L2 squared. Right? And then if you restrict the radial functions, you can ignore Q3 and P3. And so you just have to deal with Q1, Q2, P1, P2. And these are the 4 directions on the Z manifold that I mentioned. You have this is corresponding to phase, it's the gamma, and this is corresponding to scale. But this is a new direction, which is related to B, and this is related to beta. Okay. So by writing things like this, you'll notice that I included a 4Q. You know, why did I include 4Q here and also here, and then a little bit of this is there. I've just normalized it so that if you look at symplectic pairings, then this is canonical, except that it's not normalized. But what you have is, if you look at Q1, J inverse P1, then you get YQ2 squared, same Q3 paired with P3, then you get some number, and all other pairings with the J, has to be symplectic pairing, are 0. So that's how you arrange for this canonical form, and also the mapping properties as well. And by doing that, you get the nicest formula for the so-called Riesz projection onto the kernel. So in the business of self-adjoint linear operators, you have spectral measure and you're looking at orthogonal projections. In general, the natural projection is what's sometimes called the Riesz projection. What you do is, if you want to project onto an isolated point, or a group of points, or a section of the spectrum, you integrate the resolvent around the contour that encloses that point. And so you consider the operator P, which is 1 over 2 pi I, integrating around that contour of the resolvent, and that's Zi minus L inverse dz. And you can prove in functional analysis, you prove that this is actually a projection in the sense that the p squared is equal to p, and what's the other property of projection? P squared is p. It's a projection. Although it's not, it becomes orthogonal projection if you're talking about a self-adjoint operator, so it reduces to the familiar thing in that case. But in this case, it turns out, and this is connected to the fact that the parent equation was Hamiltonian, it becomes symplectic projection. And so if you want an actual formula for it, it becomes Pf is the sum j equals 1 to 3 of mu j, j inverse pjf times qj minus j inverse pjf pj. I'm sorry. Yeah, that's it. That's right. Now, that's a typo. So qj. And the mu's are just normalizations, so they are mu1 equals mu2 is the reciprocal of that. And mu3 is the reciprocal of this. Okay. All right, so checking that from the definition is hard, but you can check that if you plug in, if you apply the p given by this formula and you plug in f equals qj or pj for any of the 6 q's and p's, then you just get the identity. So you can check that p of qj is equal to qj, p of pj is equal to pj. And you can also check, so the other property that this Riesz projection has is that L of p is equal to p of L. It's supposed to commute with the operator. And that's, you can also check too, but that's where you have to use these mapping properties in order to confirm that. So that's how, if you have this W, all right, so the evolution of NLS at the level of W was approximately, as the Taylor expansion led us to this linear problem. And the way you understand linear evolution is by spectral decomposition. So you project onto the kernel, and that's a finite dimensional object. You study the dynamics there, and you project onto the continuous spectrum and analyze that separately. And the continuous spectrum, well, some people follow this approach for the analysis of solitary wave stability and blowup. And there's work by Soffer and Weinstein and Kukanya and Buslev and Perelman, and they all do this. They just do a full analysis of this non-normal operator. You fully understand the discrete spectra and also parameterize the continuous spectrum with a so-called distorted Fourier basis. And then you do Fourier analysis for the continuous spectra, which is analogous to the usual Fourier analysis, except it's not translation invariant. You have to use, you have to replace e to the ixc by some other family, which sort of parameterizes this continuous spectrum. And then you can prove dispersive estimates with that. So it's really a very elaborate and technical business. In fact, the first proof of this log-log law for blowup was by Galina Perelman, and she did that. She did exactly that. She did the full analysis of this linear operator. Merle and Raphael then wrote a series of papers in which they proved the log-log law, where they sort of bypassed to some degree a full analysis of this linearized operator, and instead found the Lyapunov functional, which simplified the analysis. And so, but still, you still have to understand the kernel to do anything, I think. Okay. So we're going to continue next time with the discussion of Z. So this suggested to us we were missing these two directions represented by B and beta, and we should, instead of looking at Q as the base object, consider Z. So Z solves this so here's the equation for Z. So this equation was originally arrived at through more ad hoc means. In fact, Zakharov had proposed a form for supercritical blowup that is just an ansatz. So you plug into the equation and it ends up with an equation of this form. So that the people were studying this kind of equation before the log-log law for L2 critical blowup was fully understood. And what happens is that you can transform, because this lambda operator is a little awkward. So you put in this quadratic phase, and then you get an equation for chi, and it's a more customary Schrodinger type equation. And now, we'll take beta equal to 0. It's actually not as important as the b for simplicity, although you can kind of merge the b and beta into 1 with this kind of transformation. But, so what you get is a 1/4 b squared y squared chi. And so that comes from that term. And then this one, we still need a sigma. And so you would think you'd be just fine without this extra term, but this term is included on purpose so that this chi has the right behavior at infinity, which gives you a z that has finite energy. So it turns out that, we'll explain this next time, it's a nice analysis that as soon as you get far away from the origin, the nonlinear term becomes negligible, and you have a linear equation. What you have is minus Laplacian minus a harmonic potential. So it's the backwards from what you're used to, right? It's a potential well that is inverted, but you can still do WKB type analysis and understand the behavior. And in order to generate the correct behavior at infinity, which gives you a z that has finite energy, you can interpret that in the chi as being outgoing at infinity. You need to take sigma equal to approximately b to the minus 1 e to the minus pi over b. It's approximately. All right, because what we have could be interpreted as a nonlinear eigenvalue problem. Let me put the plus chi there. Well, no, let me put it I'll put it equals minus 1 minus I sigma chi. And, sorry, actually, in this so if this is a locally like Q, then what you have is a well. So Q generates an inverted well, but that's localized. That's exponentially localized. And then this extra term, and b is very small, and eventually it goes down. And then you're looking for an eigenvalue minus 1. And you choose this complex component to get the correct outgoing radiation condition at infinity. And you do this, you figure out what the correct sigma is by a WKB analysis. And that's absolutely essential, in fact, to getting this log law, because the evolution of b is correlated with sigma. And that's why it was so hard to figure out. So it was figured out by Papanicolaou, Lammin, Sulem, and Sulem in 1988. And actually, there was an earlier paper by a Russian Freiman who had the right idea. But I think the story is there's a mistake in the translation, and so it wasn't realized that he had the right answer. And his paper was a year or two earlier. So Russians always like to point out that they did it first, right? And then Zakharov and collaborators gave a different explanation, which is the one that I give in '92. And Zakharov writes in that paper that it was open for 17 years. So I guess that means that he first proposed the problem 17 years before that. So yeah, so it was hard to figure out, but I eventually cracked it. So we'll discuss, next time we'll discuss how you arrive at this value of sigma. I'll kind of give an overview of that calculation, and then why the evolution of b is coupled to sigma, and then how you get the log as a result. And some aspects of the rigorous proof, and then some of my own work in the supercritical case. So see you tomorrow.